Hello everyone and welcome to another AP Calculus AB Solutions video. This video contains solutions to another outstanding 2020 practice FRQ created by the brilliant Mr. Bryan Passwater. So let's go ahead and get to it. All right, so this AB2 question, we are given a table of f prime of x values. So this is our velocity function that we're given, okay? Now it says, for x's that are between, including -2 and 10, the function f is twice differentiable, okay? And that the second derivative is positive. All right, so selected values of this f prime of x are given in the table above, and it is known that f of 7, aka our initial value that we will see at a later time, is going to be input is 7, the output is 4. So you could say like the xy point on f of x is 7, 4. All right. All right. So part A says approximate f double prime at -1. So we're going to find f double prime, and it says approximate. So this is that f prime of c is equal to f of b minus f of a interpretation, as far as the instantaneous rate of change is equal to the average rate of change, aka the tangent's equal to the secant. But this is talking about f double prime. Okay, so this is the second derivative now analyzed between the difference between the f primes. Okay, so if I'm looking at this and we're looking between the values of -2 and 7, basically my b value becomes 7 and my a value is going to be -2. So when I set this up, I'm going to be looking for the following. This is an approximation existing between 0 and -2. That's my -1 right here. Okay, so in a sense, we have our y2 minus y1 over x2 minus x1, which in this case, yep, it's the f prime minus the f prime because we're looking for the f double prime. Okay, so that we have f double prime of -1 is equal to, well, f prime of b, which is going to be our -2, aka our y2, minus our y1 is -8, and it's over this 0 minus a -2. So two negatives make a positive, so that will add to get me a 6 over a +2, which yields the answer of 3. Okay, so that's the first part. All we wanted to do was find and approximate f double prime at -1. And then the second part says, is there a time between -2 and 7 at which this derivative at this c value or at a c value equals this approximation? Okay, so we're trying to find between, let me go ahead and highlight that, between -2 and 7, is there a c value where f prime of that c would actually equal this 3 value here. Okay, so let's go ahead. This deals with, of course, intermediate value theorem. Okay, so the first condition of IVT, so we'll put over here per IVT. The first condition is that the function is continuous. Okay, so it is continuous, and we're talking about f prime, that is. We know f prime is continuous on -2 to 7. And we know that it's continuous on -2 to 7 because here it said f is a twice differentiable function. Okay, so if it's differentiable, automatically it is continuous. Okay, so f is continuous and so is f prime. So number one, f prime is continuous on -2 to 7. Number two, f prime is differentiable. So it's differentiable on -2 to 7, non-inclusive. Okay, and we know this because it just right there again stated that it was twice differentiable as far as f of x is concerned. All right, so our third stipulation with IVT is to check, are the y values different? We have to check, is f prime of -2, is it equal to f prime at 7? Okay, that's what we have to check. So let's go ahead and find f prime at -2. So f prime at -2 is going to be a -8. So we have -8 here. And then f prime at 7, so let's do this one now. F prime at 7 is going to be an 11. And we know that negative 8 is not equal to 11. So yes, we can fit a number in between those values, which in this case, we're going to say, let that y value, otherwise let k equal 3. This 3 that we got for the first part of A. Okay, so now what we're going to do is, because 1 was true, 2 was true, as far as the part to IVT, and 3 was true, all conditions were true, then we're saying there must exist, okay, there must exist some kind, I'll go ahead and write it out, there must exist a C value, a C value on negative 2 to 7, where f prime of C is equal to 3, okay? And again, this is all per IVT. All conditions were met, and we know that K, that value of 3 that we got from over here, is of course in between these Y values. Because K is in between negative 8 and 11, we know that there must exist a C value on negative 2 to 7 where f prime of C is equal to 3. Okay, so let's just go ahead and write that. We know that the third condition shows that these are not equal, but we also have to show that negative 8, okay, is going to be, or 3 is between negative 8 and 11. So let's go ahead and show that condition before we go ahead and say there must exist. All right, so now let's go to part B. Part B says evaluate the following integral. Okay, so it is a little bit involved. Let's go ahead and break it apart. I'm going to make some room right there by erasing that. And it says, evaluate the integral from 0 to 3 of the following integrand in respect to x. Show the work that leads to your answer. Okay, so first of all, what should be catching your attention is the fact of we're going to integrate f double prime of that. Okay, now f double prime of this is already showing signs of a u substitution because it's not simply just f prime of x. So u substitution, we're going to say, is x squared minus 2. So du is 2x dx, and the rewrite is going to be the 1/2 du is equal to x dx. So over here in our original function, where I used to have x dx, I'm now going to replace it with 1/2 du. So let's go ahead and constant multiple roll. Let's go ahead and constant multiple roll this 5 out. And then this 1/2 is going to make this 5 into a 5/2. And where there used to be this x dx, we're going to have this 1/2 du. Okay, and now what we're left with is simply the f double prime of u. So we have f double prime of u in respect to u, the 5/2, and last but not least, we just have to change our limits of integration by plugging 0 into our u sub to get a negative 2. And then we're going to plug in our 3 into the u sub to get 9 minus 2, which is 7. Oops. So this is our rewrite right here for part B. Now we're ready to integrate and see what we get. Okay, so the integral of f double prime, let me go ahead and make a little bit more room. Oops. I'll do it this way. The integral of f double prime is going to be equal to f prime. So we have f prime of u, and this is evaluated from negative 2 to 7 with that constant multiple rule of 5/2. Okay, so this is going to become, per first fundamental theorem, f prime of 7. So f prime of 7, f prime at 7 is 11. So it's 11 minus f prime at negative 2. So f prime at negative 2 is a negative 8. So if I'm subtracting a negative 8, it's simply going to be adding the 8. So that we have 19, and then we're going to multiply that by this 5/2 that was out in front. So 19, we have 5/2, we have times 19. We know 19 and 2 do not cancel. Okay, they're not reducible there. So we're just going to multiply 5 and 19 to get 45 and we get 9 over 2. So 95 over 2 would be the answer for part B. All right, so let's go ahead and move on. Let's look at C. It says the function g is defined by the following. So g of x is equal to this stuff right here. It says find all the critical values of g of x. So already I'm already thinking of critical numbers of g of x mean when g prime of x is equal to 0 or undefined. Okay, and classify each as a local minimum, maximum, or neither, and justify your answer. Okay, so first of all, we have to find what is f prime of x. Okay, or sorry, what's g prime of x? Because that's what we're looking for to see when does it equal 0 or undefined to start off. So what I'm going to do is end up differentiating this function of g of x. So let's go ahead and begin that part. So we have g prime of x. We have some chain rule going on here. So it's going to be f double prime of the stuff, and it's going to be multiplied by the derivative of that inside piece. So we got to multiply by the derivative of 2x cubed minus 9x squared. Okay, so let's go to multiply that, and we get, let's see, 6x squared minus 18x, with parentheses are, of course, important. So this right here is our g prime of x function. And we want to know, like we said before, when is this function 0 or undefined? Okay, so let's go ahead and set all of this that we just found to 0 or undefined. We're going to start with 0. So let's set that equal to 0. We know multiplication exists here. So that's simply saying, when does 6x squared minus 18x equal 0? And then also it's saying, when does f prime by itself, or sorry, f double prime, let me color coordinate that to match up. When does this second derivative of 2x cubed minus 9x squared also equal 0? Okay, so let's find this first one to start off. So we have 6x squared. So we have 6x is going to be GCF'd out. We have x minus 3. So that we have x is equal to 0 and 3. Okay, so we have 0 and 3 for that first part. Now we got to see when is the second derivative with this input value equal to 0. Okay, well, we have to remember one thing real quick, is the fact that this f double prime, we can find the zeros if we wanted to find those x values and list them in addition to this, or we'll just list out 0 and 3 and then test the signs with that. And that's actually what we're going to do for this problem. Let me show you why. When it showed that f is twice differentiable up here in the original problem, it also mentioned that f double prime was always positive. So if it's always positive, I can look at this thing right here as simply being always positive. Okay, so we don't in fact have to find when those x values would be 0. Okay, so positive times this is simply still going to be this 6x squared minus 18x is equal to 0. So the only critical points that we are going to have are 0 and 3. Now we just have to see, are they local minimum, maximums, or neithers by checking the signs that exist in between. Okay, so we have g prime of x. And this is our function right here, g prime of x. We know that it's always positive, so we can just view these test points on this 6x squared minus 18x is equal to 0 piece. Okay, so let's pick a number right here between negative infinity and 0. Let's say we picked negative 1. Okay, so I'm going to take a negative 1 and I'm going to plug it here and here into x. So negative 1 squared is a positive. Negative 18 times negative 1 is a positive 18, so we know it's going to be a positive. So let's pick another number in this interval. Let's pick 1. So if we put 1, again, where these x's are, we have a positive 6 minus 18, we get a negative. And all we care about are the negative or positive values, okay? And then the last interval, we can pick 4. When we plug in 4, we get 16 times 6, a very big positive number, okay? So again, we chose 4, so we have 16 times 6. So we have what, 96? And then if we put 4 in here for 18 times 4, we have 272. Obviously, 96 minus 72 is still a positive. So that's just a little bit of scratch work there on the side. So these are my signs for these intervals. And it wants to know local max, min, or neither. Okay? Since I'm looking at the derivative, which is g prime of x, of this position function, I know that g of x is increasing and then decreasing and then increasing again. Okay, so this increasing to decreasing shows that there's going to be a relative max at x is equal to 0. And then decreasing to increasing means there's going to be a relative min at x is equal to 3. Okay, so the way we're going to word that is we're going to say g of x has a relative max at x is equal to 3 because g prime of x changes from positive to negative. And then we'll go on to do the other part, that g of x has a relative min at x is equal to 3. Whoops, I realized what I did wrong. Some of you are probably like, what is he doing right now? At x is equal to 0 was where the relative max occurred. The relative min is at x is equal to 3 because that is when g prime of x changes from negative to positive. There we go. All right, so let's go ahead and keep going to part D. All right, so part D says, use a left Riemann sum with 4 subintervals indicated in the table to estimate f of 0. So we want to know what is the value of the y value of f at 0. Is this an overestimate or is it an underestimate? Okay, so let's go back to our problem that was given, and we're going to concentrate on this given y value that f of 7 was known to be equal to 4. So we have f of 7 is 4, and we're wanting to know what is f of 0. So this definitely screams first fundamental theorem, okay? If we're wanting to know f of 0, we can set up an integral that says from 0 to 7 of f prime of x in respect to x is going to equal f of 7 minus f of 0. This is just first fundamental theorem. Okay, we know that f of 7 was 4. So we can go ahead and replace f of 7 with 4 because we're trying to find what is f of 0. Okay, so we like to have our coefficients positive in a lot of regard when we're looking for these variables. So we're looking for f of 0. So let's move it over here to the left side and we'll just say a positive f of 0 is equal to this 4. And now we're going to take this huge integral, we're going to move it to the right side by subtracting and getting 0 to 7 of f prime of x in respect to x. Okay, so the written key does show a little bit different, but this is just another way of setting it up. The key did show of setting it up starting at 7 and going backwards. And yes, we use limits of integration by flipping those limits of integration, and then adding a negative so that the zeros on the bottom, the 7's up top, and then you're accounting for that negative. But guess what? We still have that right here. We just set it up from least to greatest to begin with. Okay, so either way, you're going to get the right answer. You're going to be okay. But let's go ahead and finish this up. So we need to find what is the integral between 0 and 7 using a left Riemann sum with 4 subintervals. And we're going to look at f prime of x. Well, that's what we were given. So we want to start at 0, okay? That's where it shows, and go all the way to 7 with 4 rectangles. So 0, 3, and 4. Those are the rectangles that we're going to build with our Riemann sum to figure out what is the area underneath the curve. Okay, so the area underneath this graph is going to be left Riemann sum. So here we go. The first jump, if you will, is 2. So it's the dx is 2, and the y value, since it's left, is negative 2. Okay, this jump shows a jump of 1 with the y value at positive 2. This jump is 1, and it shows this y value here of 6, and then this dx is 3. Okay, and this one's going to have a y value of 8, because again, we're doing left Riemann sums. Let me make an 8 right there. We are adding these 4 subintervals together, and this is going to show that area underneath the curve that's basically from 0 to 7 of f prime of x dx. That's what all of this is going to show. So let me go ahead and grab all of that, and I'm going to take it all the way down here. Whoops. I think I will copy it instead for the sake of time. And I'm going to put it way down here. All right, so let's see what we got as far as this area underneath the curve is. So we have -4 plus 2 plus 6 plus 24. So -4 plus 2 is a -2 plus 6 is a +4, so that we get this 28 is what that area is going to be. So 28 is what we get for this part right here. Okay, so to be 4 minus 28 is going to be f of 0. F of 0 is finally equal to 4 minus 28. So f of 0 is going to equal a -24. Okay, so now that we have that, let's go ahead and move on to part E. Oh, wait, first of all, we have to figure out if it's an over or an underestimate. Okay, so looking at this left Riemann sum that we did here, which equaled 28, we have to ask ourselves a couple of things as far as what this entailed, okay? First of all, with it being a left Riemann sum, we're going to say that this is going to be an underestimate, okay? And it is an underestimate because f double prime was told to us that f double prime was positive for all x, okay? That meant f prime was increasing for all x, which means this second derivative could be seen as a positive, showing that it was concavity upward. Okay, so concave up. And then increasing, so we have an increasing function that was concave up, and it could look something like this, if you will. So if we were doing left Riemann sums, and it was increasing the entire time concave up, and we were talking about from this 0 to 7, okay, so from this 0 to 7, we're talking about this area is what we found. We're using left Riemann sums. Just visually, you can see that this is going to be an under approximation of some kind. Okay, so what we're going to say is since f double prime was positive for all x's, that means f prime was increasing for all x's, then the left Riemann sum is going to show an under approximation. Shows this 0 to 7 f prime of x dx as an underestimate. So underestimate. Okay, so now let's go to the very, very last part, part E. It says, let y equal h of x be the particular solution to the differential equation. Okay, so we do have a differential equation right here that's given, and we are used to seeing h of x is the particular solution, and some of us might already be going to the route of, oh, we're going to do separation of variables, we're going to solve, we're going to use our initial value, we're going to solve for our constant of c, and then find y all by itself. But this one's actually even clever. It's even more clever than that. It says, with the initial condition, h of 2 is equal to -1. On the axes provided, sketch a slope field for the differential equation first, and then we're going to use the tangent line to h of x at positive 2 to approximate 2.1. So we need to read the problem because we're actually not going to solve this particular solution all the way back to a y equals or h of x equals. And if you do, you just wasted some time. So please make sure to read the problem. If it said solve the particular solution and actually solve it out, then you would do the separation of variables. Okay? So what we're going to do is we're going to go ahead and find at these 9 points. Here we go. We have one. Let me go ahead and highlight these. I'll highlight them in gray. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to use this differential equation to find the slope. Okay? So if y is equal to 0, here, here, and here, then we know that right here when I'm putting it into our differential equation, it's going to 0 out. So 0 over negative 2 is going to give you a horizontal tangent that looks like this. Remember, we're doing many slopes on this slope field, so we're just drawing them out. Okay, so now let's pick this one. This one is 0, 1. So 0 would go in for x. 1 would go in for y. Okay, so 0 in for x, we have f prime of 0. And f prime of 0 up here was negative 2. So f prime of 0 is a negative 2 times the y value. Again, we're using this point of 1. And it's going to be over 2. The x is 0, so it's times negative 1. So I have a negative 2 over a negative 2 is going to be a positive 1. Whoops. So at 45-degree angle, we can go ahead and write this mini slope of a positive 1. Okay, so now let's try this one. So this one's 2, 1. This one's 3, 1. Okay, so real quick, we're going to come over here. We're going to put in our y values, again, using our differential equation. They're going to be 1 and 1 for both of those. So I'm going to do these simultaneously. Our x value was 2. So that's 2 minus 1 is 1. 3 minus 1 is 2. And then now we just have to find what is f prime at 2 and f prime at 3. So f prime at 2 was 2 and 6 for 3. So 2 and 6. So we have a 2 over 2, which is another 1. And then we have a 6 over 4. Okay, so 6 over 4 reduces to 3/2. So like 1.5, if you will. Okay, so let's go over here, whoops, in our slope field, and we're going to show another 1, but then one just a little bit steeper because it had that 1.5 feel to it. Okay. So now let's do these other points. I have a 0, negative 1. I have a 2, negative 1. And then I have a 3, negative 1. Okay, so let me go ahead and make room for that right here again. And I'm just going to find those slopes at those specific points. Okay, so if 0 is x, we have negative 2 on the bottom. And f prime of 0 gave us negative 2. And then our y value here was a negative 1. So we have 2 over negative 2. We're going to have a negative 1. Okay, so let me go ahead and do that negative 45-degree angle, if you will. Okay, so now let's move to negative 1. So x is 2. So we have 2 minus 1 on the bottom is 1. So we have a positive 2. F prime, again, I'm plugging in this x value where I see an x. So f prime of 2 is going to be a positive 2. And then our y value that we got right here from this point is a negative 1. We're just going to go ahead and plug that in right here and see what we get. So negative 1 times 2, this is going to be a negative 1 as well. So negative 1 is negative 45-degree angle. And then our last one is going to be at 3, negative 1. Okay, so again, we're going to plug in 3 as our x into our differential equation. Okay, so in the denominator, we have 3 minus 1 is 2 times 2 is 4. And then we have f prime of 3. Well, f prime of 3 is 6. So we have 6 here. And then the y value that we got was another negative 1. So that you see another negative 6/4, which is negative 3/2, which is negative 1.5. So it's going to be just a little bit steeper than that negative 45, a little bit more negative, if you will. So that's the first part. Now all we have to do is use the tangent line to h of x so that we can approximate h of 2.1. Okay, so we need to develop an equation of a tangent line of y minus y1 equals m times x minus x1. Otherwise, y minus h of a is equal to h prime of a, because again, we're trying to approximate h, and it's going to be x minus a. Okay, so our a value is this input of 2. That's going to go here, here, and here. So we want to know, okay, so x minus 2, what is h prime at 2? Okay, h prime of 2 is going to be, first of all, we know what h of 2 is because it was given to us right here with this initial condition. It's -1. So it's y minus a -1, which is just adding 1 here on the left side. But if I want to know what is h prime at 2, I'm going to look on this function that we were given as far as this slope field with the differential equation, and I want to find at 2. So it's the same as saying h prime at 2. Well, over here, h prime at 2 with the y value of 1, okay, so this input is 2, that output is a -1. I'm specifically looking at this one right here, that point. And at that point, I knew from before when I did the slope field that that slope was a -1. It was at a -45-degree angle. So very, very clever how this was awarded and how you had to find this h prime at 2. Otherwise, you might have been prone to go up here and say f prime of 2 is equal to this +2. Okay, we're not looking for f prime. We were looking down here for h prime. So very, very clever question. Okay, so now we're just going to approximate our 2.1 by plugging in our 2.1 right here. And that would give us our y value. So we could say a -1, 2.1 minus 2, and then subtracting this one over, this is going to be our approximate value right here. Remember, you don't have to simplify if you do not want to, but just 2.1 minus 2 is going to be a 0.1 times this -1 is a -0.1, and we're going to subtract this -1 so that the answer would be a -1.1.